Similarly to the resistors and to the inductors, there is an analogy of capacitors in the hydraulic terminology. Here we can use a dam to represent the blocking of the voltage from the upper level to the lower level across the dam, and the current is the current going through the dam and passing from the top level to the lower level. Going back to the laws of physics, we can have a look at Gauss' law, which describes the charges and their relation to the displacement field, which is a closed loop integral over a surface path, two-dimensional geometry here, along a closed surface, which is A. That means all the charges tunneling through a defined area A. So if my arm here would be representing a defined area, then all the charges going through here would be counted inside this equation. Then we have another law from Faraday, which describes the voltage as a function of the electrical field. And here it's integrated over a one-dimensional surface, the path of a loop, where L is the length of the loop. Putting these two equations again into Ohm's law and remembering that the current can be derived from the charges, we have Ohm's law here first, which is the integral of current over time divided by the voltage across the resistor. And we can replace the current through the capacitor by the time derivative of the charges flowing through that capacitor. That means the integral over time cancels out with the time derivative here, and we have the definition of the capacitance, charge stored per voltage, as engineers tend to express it, and putting in Gauss' law up here and Faraday's law at the denominator, we have the relation to physics. Again, we have a dependency on the material that is used. And for homogeneous and linear materials, we can again simplify here the integrals and simply replace them by multiplications, where epsilon is the permittivity and the rest of the equation defining the capacitance of a capacitor is represented by its geometry. In terms of the dam, this one would be replaced by the thickness of the dam, which would be the distance here, the d, and A is the surface of the dam. So the bigger the surface is, the more charges, the more water molecules the dam could withhold, the more charges a capacitor can store. And the thicker the dam is, the more distance you have between both ends, both sides of the dam. The bigger the distance is between the plates of a capacitor, the more voltage that capacitor can withstand. So simplifying everything what we've just written down here, is the capacitance is defined as charge stored by voltage, which is the permittivity times the surface of the plates divided by the distance of those two plates. Having a DC current through our capacitor would be equal to having a big hole in our dam. So we would actually lose all the charges, all the water molecules that we're trying to hold back with the dam. And that is because the voltage across the capacitor is the integral of the current through the capacitor over time. And if this integral is integrated over a DC current, the integral would go towards infinity. That means also the voltage would go towards infinity. That would mean that the water pressure, the voltage would collapse at some point. So we can never have any DC current through a capacitor, as we cannot have a continuous water flow through a dam. The instantaneous energy stored in the capacitor is the integral of the instantaneous power represented by the voltage across the capacitor and the current flowing through the capacitor at that exact amount of time. Representing the current through the voltage, through the derivative of the voltage and multiplying by the capacitance, which is Ohm's law applied on the capacitor, we end up with the partial integration integral over here, where we have Vc at a specific amount of time times the derivative of the same capacitor voltage Vc. And then we integrate the voltage across the capacitor times the derivative of the capacitor over time t. Now that integral can be expressed from a mathematical point of view as a partial integration. X times the derivative of x would end up being represented by itself and an offset, which is x squared. Now putting the right side of that equation back to the left side of the equation, we would end up having that exact same integral twice on the left side, and on the right side we are left with x squared. And if we bring the factor of 2 back to the right side of the integral, we end up with the solution for this integral represented by this equation. Now replacing x with the voltage across a capacitor, and the derivative of the voltage replaces the derivative of x, we can rewrite the x squared divided by 2 with the voltage squared divided by a factor of 2. And originally we had the capacitance outside the integral, so that one stays here. And therefore we have the final equation for the energy stored in a capacitor at a given time. The symbol, the electrical symbol of an ideal capacitor looks like that. But you can never get a capacitor without having the leads connecting the plates to the rest of the circuit, which are actually representing an extra resistivity. And that extra resistor is then also representing another inductor, because there would always be a magnetic field around any inductor. And as we are dealing with AC current through the capacitor, would lead through an AC current through the resistor, and therefore a magnetic field around that resistor, around the leads for the capacitor, which represents another inductor in series with the capacitor. Now, having these non-ideal behaviors in mind for a capacitor, there is an exercise for you. Having a capacitor of 470 microfarad and given with a series resistance of 10 milliohm. What is the magnitude of the impedance of this circuit at 70 kilohertz? So the series connection of the capacitor C with its equivalent series resistance of the 10 milliohms. And then let's have a look at the exact same information, but not just on a single frequency, but in a frequency range from 1 kilohertz to 1 megahertz. In any kind of circuit simulator that you prefer, or any math tool that you prefer, using the equations for that, we got the magnitude and the phase of that capacitance over frequency. I can recommend to do that in a circuit simulator, but T-Spice is very well suited for that. If you prefer to use any other math tool or circuit simulator tool, feel free to use your own favorite tools. Now going one more step further towards a real capacitor and dropping the simplifications, we can add another inductor here, an equivalent series inductance of 10 nanohenry, and just compare what happens to the plots that we have plotted up here in the B part of the exercise. If you fancy to do any extra exercises, you can start to play around with the given parasitic elements, the ESR, the equivalent series resistance. For example, you could turn it into a 1 milliohm or whatever you like. Just try different values and see what happens. And the same with the equivalent series inductance. You could change the 10 nanohenry into 100 nanohenry and see how that changes the results for your capacitors. If you want to go even one more step more realistic, try to go on the internet and find some data sheets for different capacitors and reuse the values of ESR and ESL that you can find there and put them in your simulation. Maybe you can even find some graphs in the data sheets which are comparable to your simulation results.